Hi my students, it's lesson 55, Algebra 1. I'm excited. We're going to do a really fun lesson today, complex fractions. You are going to feel so smart. And I think, if memory serves, this is the first time this class has done anything like this. 55.1, let's jump right in. Let me show you what a complex fraction is. A complex fraction is something like this. This is a super simple one. It's got more than one division bar. That's what makes it a complex fraction. It's got more than one bar, if you want to call it. That's what we do. You're cool, you're a mathematician, you call it a bar, not just a line, man. So more than one division bar means it's a complex fraction, and our job is, we don't want to have multiple bars, we want just one bar. So we're going to fix that. Now, one thing I want to say about these problems is sometimes it's hard to keep track of which lines are the bigger lines, right? This is the bigger line, this is the smaller line. So this is a fraction in the numerator and just like a whole number in the denominator. Sometimes it's hard to tell. John makes his a little bit darker. You can usually tell in the book, but make sure that in your own homework you make a very distinct difference between those so that you won't confuse yourself about which is the big bar and which is the little bar. Okay, when we're dealing with a complex fraction problem, we always start by looking at the denominator. And we want to turn the denominator into a 1. There's a fancy one for you. The reason we want to do that is because whenever our denominator is a 1, we can ignore it, right? Poof, it disappears. A denominator of 1 goes away, and that's exactly what we want. We want this to go away so that we just have a fraction on top. Okay, cool. So how do we turn it into a 1? We use reciprocals, because anything times its reciprocal equals 1. So first let's make this a fraction so that we can make a reciprocal of it. And what would this reciprocal be? Well, we just flip it. 1 over c. Oh, look what's going to happen now. When we multiply this, we're going to get c over c, which is equal to 1, and poof, this is my poof notation, poof, it disappears. We no longer have a denominator. Praise the Lord. Okay, that is great. However, when we multiplied by 1 right here, we did it to the bottom, but we have to do it to the top as well, right? This has to equal 1. Just like any time we multiply the denominator of a fraction, we have to multiply the numerator as well. So that means our final answer is a over bc. This isn't our answer, this is our 1, right? Our stovepipe hat, Abraham Lincoln, come to life in our problem. This is our final answer. Make sense? Let's do another one. Over 1 over b. Notice my exaggerated line. Multiple bars, we have to get it down to just 1. We start with our denominator, and we want to turn our denominator into a 1, and we're going to use a reciprocal to do that. So 1 over b, I guess I want to multiply it by b over 1. That will turn into b over b, which turns into 1, which poofs. You don't have to write this up every time, but in the beginning, go ahead and write it all out. Now, this b over 1 has to be multiplied by the top as well. Hannah Cranny is not going to be happy if we don't. So, our final answer is b over c. Beautiful, right? Now, there's another thing that John always writes at the beginning of these problems. At this one, he wrote this: c and b are not equal to 0. Now, why did he write that? He wrote that because if this was 0 or this was 0, we would have denominators of 0 and the kingdom would implode, And we can't have that. We can't let that happen. So he gives us a little note here in the beginning saying, don't worry, I'm not going to let that happen. Up here he said the same thing. He said that B and C, because C was the denominator of the original fraction, B and C are not equal to 0. So that's why he says that he's floating, and it just makes our lives easier. It's one of those kind of annoying and scary looking things that he puts at the beginning of the problem that you think, what does it mean? Does that hurt me? And it doesn't. It makes life easier. Okay, next problem. A over 1 over C. Okay, this one looks a little different. It's weirder on the bottom and easier on the top. It's fine, don't worry. We turn our denominator into a 1. We use a reciprocal. C over 1. That gives us C over C, which is equal to 1, which poofs, and we no longer have a denominator. However, we multiplied here, so we have to multiply in the top. Now, here it was important to use the 1 because we wanted it to be the reciprocal. But here, because we don't have a fraction, I'm just going to write it as a plain C. It's the same. This is exactly the same. It's just a different notation. So our final answer is A times C. These were all right. I don't know why I feel better when I'm sure that I checked them. All right, so we can put the C in the denominator, we can put the C over 1, or we can just write the plain C. These are the same. Abraham Lincoln approves. Okay, 55.4 on the back. A over X over B over A plus X. What the heck is this? All right, that looks weird. Since when do we have pluses? All right, well, you know what? We're not going to let it rattle us. And again, John is nice enough to say that X cannot be equal to 0, and B cannot be equal to 0, and A plus X cannot be equal to 0. So he's covering all the bases for us, making sure that our kingdom stands strong. Okay. We're going to use, even though this denominator looks weird, we're going to use our very same approach. We want to turn this into 1. We use a reciprocal to do it, so that means we flip this. And we're going to multiply that. Now, before I go on and make sure that that equals 1, I'm going to write it up here. Now that you understand a little better what we're doing, I want you to make that up and, make the notation that you need to multiply top and bottom right away before you forget. All right, this becomes B times the quantity A plus X over B times the quantity A plus X. It turns into a 1, and it poofs. It disappears. It's a 1. Our denominator no longer exists. Now I have to do my numerator, which I've already set up. This is my and now I just need to multiply across. I have A times the quantity A plus X over, alphabetically, B times X. And this is the correct answer. There's no need to distribute this A across the binomial A plus X. Distributed or undistributed are equally acceptable. All right? So that's our final answer. Section of this lesson summarizing what we're doing here, that we always take whatever is in the denominator and we flip it and multiply, and it's reminding us that there are 3 rules of algebra. The first one, it's this rules of algebra. The first one is called the additive property. This is shorthand. Additive property. That means that when we have an equation when we have an equation, thus the word equality here, we can add or subtract any number as long as we do it from both sides. Then we have the multiplicative property of equality. The word equality reminds us that these relate to equations. Okay, so the other rule with equations is that we can multiply or divide the same number to both sides as long as it's non-zero, because 0 causes problems with division, right? So we got to be careful and not use 0 when we're using the multiplicative. But we can multiply or divide both sides of an equation. We do it all the time. We can multiply or divide to both sides, and we're cool. The third one is the one that we're using here, and that is called the denominator / numerator, same quantity rule. And that's the one we are using in spades. It's exactly what this is, right? Denominator and numerator are being multiplied by the same quantity, so everything's good. So this is just a little theoretical explanation of what we're doing and why it's okay. But you know what? Complex fractions are fun. You're going to love them, and just remember you're using that third rule of algebra whenever you simplify complex fractions. I'm done.